Okay, so today we're going to be talking about this thing called related rates. Last time I introduced a scenario in which a silly monkey was messing around and kicked a ladder and made the ladder slide down a wall, right? And we talked about how we could use implicit differentiation to talk about the rate of change of y with respect to x, where y was the vertical distance from the top of the ladder to the floor, and x is the horizontal distance from the base of the ladder to the wall. Okay? And at the very end of class, I mentioned be careful how you describe this situation because it's really, really easy to want to introduce words like faster and slower, where we're inherently introducing this notion of time when we talk about those words. Okay, well, that's not necessarily a bad thing, right? A lot of things do happen in life, right? So time is naturally involved. So let's think about this scenario where we do take into account time, okay? So I'm going to, so this is what we did last time, right? So we had this falling ladder where we could relate the scenario, the quantities x and y, which were as I just described, and we were able to find the rate of change of y with respect to x, okay? Now let's imagine that we do want to talk about time in this situation, okay? So let's imagine that x is actually a function of time, okay? So let's say that the base of the ladder, so remember x is the distance from the base of the ladder to the wall, okay? Let's say that that distance is changing at a constant rate, okay? And so I'm gonna call v is the constant rate that the base of the ladder moves away from the wall. Okay? Is everybody okay with that so far? So I'm just introducing a time element here so that we can talk about it. Okay, so if I wanted to talk about the rate of change of x with respect to t, what would that be? The rate of change of x with respect to time? Well, so x of t is a linear function, if you look at x of t, right? But I want to know the rate of change of x with respect to time. Arian? Would just be v, right? Notice that I wrote v is the constant rate that the base of the ladder moves away from the wall, right? So v is the rate of change, the constant rate of change of x with respect to time. Okay? Are we awake? It's Monday. How are we doing? Okay? All right. So I can record that fact, right? So when I'm using this x prime notation, right, I am talking specifically about the rate of change of x with respect to time, right? Okay. So now, if x is dependent upon time, well, that sort of forces the entire scenario to be dependent upon time, right? So we can also talk about y being dependent on time, okay? So if I wanted to, I could rewrite my original equation so that x and y are now both dependent upon time, okay? And I can once again talk about the rates of change, right? Only now instead of talking about the rate of change of y with respect to x, I want to talk about the rate of change in this scenario with respect to time, okay? So if I take the rate of change of x of t squared with respect to time, what do I get? Would this help if I wrote it this way? So I want to find the rate of change with respect to time of this this thing. Okay, I see one person trying right now. Are we here? Are we participating? What you got? Yeah. Okay, 2 times x of t, so that's the power rule, right? Times the rate of change of x with respect to time. That's the chain rule, right? Okay. What if we do the same thing to y of t squared? What do you get there? Boucher? Mm-hmm. Great, okay. And then if I take the rate of change of 100 with respect to time, what do I get? 0, okay. So we get this, right? Now, we already know what x prime of t is, so probably the interesting thing to look for would be the rate of change of y, right, with respect to time. So we can do that and solve for y prime of t. And notice when we solve for y prime, we now have an equation that also has a rate in it, right? So I've got a rate of y and a rate of x, and they're related by an equation. That's where we get this name, related rates, okay? This is where this comes from, okay? So what was the source of the related rates equation? Where did we start with in the first place? Whoop. Oh, I didn't mean to press that. I just gave you the answer, okay? So the equation that relates the associated quantities, right? We needed to start with an equation relating x and y so that we could even start finding rates of change, right? Okay, so we had to start here to get to our related rates equation. Question? Okay, so what we're doing, so we had talked about this scenario on Friday, right? And what I'm doing here is I'm introducing a time element by saying, let's suppose that x is a function of time. So remember, x is this distance from the base of the ladder to the wall, okay? And so it's very reasonable to think about it as changing with time, right? Once the monkey kicks it, stuff happens, and that stuff happens over time, okay? So I'm gonna say, let's suppose that x changes with a constant rate, okay? So that's where these statements come from, okay? And then since x is a function of time, y is inherently also going to have to be a function of time, okay? So that's why I can introduce this notation here. And the quantities are still related as they originally were, right? Just because I'm introducing time doesn't change the fact that x and y satisfy this Pythagorean formula relationship, okay? So then once we have this formula now, we can differentiate with respect to time to be able to talk about the rates of change with respect to time, okay? Is that helpful? Okay. All right. So once again, so the thing that I'm trying to draw your attention to, though, is we ended up with an equation that related rates of change, okay? Hence related rates, okay? But in order to get there, we had to start with an equation that related quantities involved, okay? Not rates of change of quantities, but just the quantities themselves, okay? And then from there, we could build to a relationship between rates. Okay. So let's look at another example. Okay. So I've got an ice cube, right? No, not an ice cube, just a cube. Sorry, I was dreaming about cold liquids. Okay, so the edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? Okay. So can you digest this problem for a second? what are we asking for, and what do we know? Okay, so we want the rate of change of volume. Okay, so rate of change of volume. Okay, what did they tell us? Rate of change of what? Yeah, great. Okay. So somehow we have to go from what they gave us, this rate of change of side lengths, to this thing that we want, which is the rate of change of volume. Okay. But do we ever just start with the rate of changes? That hasn't been our forte, right? So this is going to be a multi-step process. Okay. So what we've done so far is identify the rates involved. Okay. And so we identified that they gave us how fast the edge length is changing, and we want to know how fast the volume is changing. Okay. But once again, we never start with the rate of change. We have to start with something relating the relative quantities associated to these rates of change that we know about and want to know about. Okay? So for this scenario, what quantities are associated to the rate of change of the edge length and the rate of change of the volume? Erin? Edge length and volume, right? Yeah? Okay, so let's call the edge length S and the volume V. Okay, now inherently, once again, there is an implied time element, right? The edge of the cube, the rate of change is 2 centimeters per second, right? So there is a time element involved, but what we can do is focus on these quantities, edge length and volume, okay? But having those two quantities and just knowing that they exist isn't sufficient, okay? Remember, at the end of the day, I need to relate these quantities because at the end of the day, I know something about the rate of change of the side length, and I want to know about the rate of change of the volume. Okay? So if I have any hope of getting to a formula relating the rate of changes, then I should probably start with a formula relating the quantities. So what formula relates the quantities edge length of a cube and volume of a cube? Volume is S cubed, right? Okay. So if you wanted to not complicate the notation too much, we have here written volume as a function of side length, right? Because it is. But you could also just record volume is S cubed, okay? Because remember, what we're really thinking about in this instance is how these two things are changing with respect to time. Okay? So yes, volume is a function of side length, but side length is a function of time, so the implication is that volume is also a function of time, right, when you look at that composition. Okay? So to decomplicate the situation, I'm going to just write V equals S cubed. Okay? So now we have a formula relating the quantities. Why did we write that formula down again? What do we want? To relate the rates, related rates, right? So remember, this is why I write this stuff down. What's given and what do we want? To remind me of my end goal, right? Because we've already done like 3 things and we're nowhere, we're not done, right? So I want the rate of change of volume, and I'm given the rate of change of side length. So I have side length, I have volume, I want to know the relationship between the rates of change. So the only obvious next step is to do what? Find the rate of change with respect to time, okay? And that's the tricky part, okay? So we want to now find the rate of change with respect to time, okay? So what does that look like? Well, that requires us to use implicit differentiation. So remember when I said these differentiation rules, they're not going away, right? They're going to stick around for the rest of the semester. So you can't brain dump, can't let go of them. You need to remember them, okay? So if I want to find the rate of change of the left-hand side with respect to time, what do I get? Left-hand side of the v. So what's the rate of change of v with respect to t? Mm-hmm. Not yet. Chain rule. Okay. What does that mean? Okay. So I shouldn't have gotten into that conversation about this composition. V is a function of s, right? But it's also a function of time. Super not that complicated. Okay. So if this had been an x and you were taking the derivative with respect to x, what would the derivative be? 1, right? But this is not, so okay. And then if this was a t and you were taking the rate of change with respect to time, what would the derivative be? It would still be 1, right? Okay. So the rate of change here is 1 times the rate of change of v with respect to time. You don't even have to think about it that hard, actually, because all I wanted was the rate of change of the left-hand side with respect to time, right? So the rate of change of volume with respect to time. That's exactly what this is, the rate of change of volume with respect to time, right? That's what this notation means. Okay. Yeah. As long as you're keeping track of the fact that you're taking the rate of change with respect to time. Right? Okay. So I write dv dt because, like we said, for instance, the volume is also a function of s. So if I write v prime, I could be referring to dv ds or dv dt, right? So this keeps it to be less ambiguous. Okay. All right. What about the right-hand side? This is a slightly more complicated function of time, right? In the sense that s is a function of time, and I'm cubing it. Beautiful. Okay. So there's the rate of change of the right-hand side. And notice we have now an equation relating to rates of change. Okay. In particular, here's the rate of change that we want, dv dt. Here's the rate of change that was given, the ds dt, right? Now, okay, so there's some other things involved. That's okay. Yeah.
That's basically telling me what we have right there is that for every little, say every one change in time, we're going to have that many changes in side length involved.
So a little bit of change in time is going to cause a little bit of change in side length. But what this is saying is that the corresponding change in volume is not only impacted by the rate of change of the side length, but also the length of the side itself. Okay, so you have to coordinate all of these quantities when you're thinking about the change, the rate of change of the volume. Okay, so that's what makes this challenging, right? Is you've got, so we're now looking at way more complex scenarios. Okay, it's no longer just like one quantity being dependent upon another quantity. It's now we're looking at multiple quantities dependent upon time. Okay, and so the ways in which those can change and vary over time become more complicated. Okay, and so this is an example of that. So once again, this is showing us that the rate of change of volume with respect to time depends not only on the rate of change of the side length, but also on the length of the side itself. Okay, and so something that I heard earlier was this idea of plugging in. Because remember, there were actual values given to us at the get-go. Okay, so I waited until the end to plug in values because what would have happened if I plugged them in at the beginning? If I plug in 50 centimeters here, then volume becomes a constant. I can no longer talk about the rate of change, right? Because it's just whatever 50 cubed is. Okay, so so that's one tendency that I see students have a lot, which is to try to plug in as early as possible. Fight that urge, right? Okay, because what we want to do is we want to talk about how the quantities vary in relation to each other, and then take sort of like a snapshot in time and see what's happening at a specific moment. So if I was being really careful, what I should have said is that I wanted the rate of change of volume when the side length is 50. Okay, so now that I have a relationship between the rate of change of volume with respect to time and the rate of change of side length with respect to time, now I can say, okay, well, I wanted the rate of change of volume when S is 50, right? And now I can go ahead and plug in the things that I know. So S is 50, and the rate of change of the side is 2 centimeters per second. Okay. And notice if you actually like think about the units involved, right? 3 is unitless, but the 50 is centimeters. So square centimeters here. The 2 is centimeters per second. So there's cubic centimeters per second, right? So this is cubic centimeters per second, which should make sense if we're talking about a rate of change of volume. Okay. Yes. Mm-hmm. Yes. Well, I mean, you can talk about other things, but typically when we refer to related rates problems in calculus, we're talking about quantities dependent upon time. Mm-hmm. Yes. Okay. Okay. How are we doing? So that's just a record of what I just said. Let's do one more example, and then I've got some practice problems that we can work on, okay? So I'm giving you these examples because historically speaking, these problems are challenging, right? And the reason that they're challenging is because I give you 2 sentences and no roadmap for how to get from those 2 sentences to a solution, right? To a question. So for instance here, I've got a spherical snowball melting at a rate proportional to its surface area. Show that the rate of change of the radius is constant. Okay, right? There's no obvious roadmap here of what to do, okay? So the best you can do is try to identify the things that you are given, the things that you want, and the things that you know to help relate those 2 aforementioned things, okay? So in this case, saying this gives us some information, right? So spherical snowball melts at a rate proportional to its surface area. That says this, right? So the rate of change of the volume is proportional to its surface area. Okay, so that's from way back, right? This is proportional to. Okay. So now what we need to do is sort of figure out our roadmap, right? So this is where we're starting, up here, and we want to get to the end. So here's the roadmap, right? We were going to express the snowball's volume as a function of its radius, right? Because once again, the thing that they gave us relates is about a rate of change of volume, right? And the thing that we want to know about is the rate of change of radius. So we need to have a formula relating the volume and the radius. Okay. Now, this middle part, express the snowball's surface area as a function of its radius, that comes into play because the problem introduced the notion of surface area. Okay. So then it becomes a challenge to say, okay, so now that we've got these expressions relating the quantities, volume, surface area, and radius, now let's bring in the rates of change. Okay, and so that's where we head in this direction. And then, so finding the rate of change of volume with respect to time and relating the rate of change of volume with respect to the radius, okay, to the given information. Okay, so let's just see how this pans out. Okay, so express the snowball's volume as a function of its radius. Do you guys remember volume of a sphere? 4/3 pi r cubed. Oh, well, this is the moral of the story. It's not like the calculus that's hard, right? It's figuring out all the stuff in between that's hard here. Okay, so let's. All right, so there's the volume of a sphere in terms of its radius. Oh, FYI, I posted a PDF of a whole bunch of really helpful formulas to do these problems, things like the volume of a sphere, on Blackboard. Okay, so that'll help you while you're doing your homework. Okay, the surface area of a sphere, okay, is 4 pi r squared. That's also in that sheet. Okay, so using this first formula, how would you express the rate of change of volume with respect to time? So what's the rate of change of the left-hand side with respect to time? dv dt, right? What's the rate of change of the right-hand side with respect to time? So 4/3 pi is a constant, right? So we leave that alone because it's multiplying something interesting. So what's the rate of change of the something interesting? 3r squared dr dt, right? Because I'm taking the rate of change with respect to time. Okay? So we get this. If you simplify, the 3's cancel. Okay? But notice 4 pi r squared, we've seen that before, right? That was over here, right? So that means that we could actually say that the rate of change of volume is the area times the rate of change of the radius with respect to time. Okay, so if I plug this in here, right, I get dv dt equals a of r times dr dt. Sorry, I got cut off there. Okay, but then we also knew from up here that the rate of change of volume with respect to time is proportional to the area, right? So that's where this formula comes from. Okay. So if I compare these two things, I've got a formula for the rate of change of volume here, a formula for the rate of change of volume here. If I set them equal, right? So I'm taking this formula and this formula for rate of change of volume with respect to time, setting them equal. What do we discover? The rate of change of the radius with respect to time is a constant. And that's what we were trying to show. Okay? So you can do a lot with this, but it takes some vision, right? And that vision is to identify what you want. It's usually going to be some rate of change at some moment in time or when something is happening, right? What they told you, what was given, right, which will also be some rate of change and maybe some other stuff. Then you have to come up with a formula relating the relevant quantities associated to those rates, okay? So that you then have a formula to find the rate of change with respect to time to then proceed to answer some question, okay? So there's a lot of work on you, okay? Okay, so let's practice because like I said, historically, this can be really challenging. Okay, so I've got a handout here that's going to help us explore some different types of problems. What is some of it? Okay. So we're taking a day off from calculus, but not really, right? So you get up early to go fishing at a lake. While fishing, you toss a rock in the water. You notice that the ripples form concentric circles, which emanate from the point of impact. Looks like the radius r is increasing at a constant rate of about 1 inch per second. You take a picture with your cell phone when the radius is 3 feet and wonder how fast the circular area is changing at that point in time. So, pass them. Are there extras there to pass around? Alright, so I need some of those too. Okay, so do you have a visual image of what is happening in this scenario? Anybody else still need one? Okay, so I spoiled a little bit of the fun by answering the first thing, right? Which is first decide what you're trying to find. Okay. Well, I didn't spoil all the fun. You can still draw a picture if you want, right? So you tossed a rock. The rock hits the pond, and then forms concentric circles that get bigger and bigger, right, as time goes on. Okay. So this is sort of like not a snapshot, right, but rather an image, if you will, to help you think about the situation as it's changing, okay? And so, whoa, that's an R. So you've got the radius of the circle, which we're saying is in fact changing, right, at a constant rate of about 1 inch. So I did some of the work here for you by giving you a label already for the radius. And what are we interested in? What do we want? Yeah, we want to know how fast the circular area is changing. Okay, so what do you want to call area? A. Sounds good to me. So if I wanted to say mathematically what I want, how would I express how fast the circular area is changing using mathematical notation? dA over dt. Exactly. So I want dA dt when what? when radius is 3 feet. Okay. What did they tell us in the problem? So r is increasing at a rate of about 1 inch per second. How can I express that mathematically? Yeah.
D of r over d of t equals 1 inch per second.
Great. I like it. Okay. So what do you know that's going to help us relate the quantities? Which quantities should I be thinking about? Area and radius, right? Because I've got a dA dt and a dr dt. So what can I know that relates A and R? A equals what? Pi r squared. The 4 pi r squared was for the surface area of a sphere. Okay. So here's a formula relating the quantities, A and R. Okay, bless you. And so in order to get from what we know to what we want, what should we do? We should do calculus. Yay! Right? Okay, so in particular, I want to find the rates of change, right, with respect to time. So what is the rate of change of the area with respect to time? The rate of change of area with respect to time. It's miraculous. Okay? And what about the right-hand side? What's the rate of change of pi r squared with respect to time? 2 pi r. Is that it? dr dt, because I'm taking the rate of change with respect to time. Okay? Am I done? I'm done with the calculus part. Have I answered the question? No. So what should I still do to answer the question? Evaluate it, right? So I wanted the rate of change. So remember, I wanted the rate of change of area with respect to time when radius was 3 feet. Now I've got a slight issue here. What's my issue? Yeah, there's a discrepancy in units, right? So I've got radius is 3 feet and my rate of change is in inches per second. So if I want to be able to give a nice answer, which I would like to be able to give a nice answer, because it would be weird to say that the rate of change of the area is like some number of feet times inches per second. That would be weird, right? So let's make it a nice unit. Do you want the answer in feet or in inches? Inches? So then instead of saying when r equals 3, what should I say? 36. Okay? So then that's going to be 2 pi times 36, right, times 1. And that's going to be in inches squared per second. Okay? So help me interpret the meaning of this number again. What does this number mean? It's the what?
Rate of change of the area of the circle with respect to the rate of change of the radius.
That would be dA dr. Yeah?
It's the rate of change of the area with respect to time.
When? When the radius is 3 feet. So all of that's important, right? Because notice this formula right here tells us explicitly that the rate of change of area will be different depending on how big the radius is, right? Because radius is in this formula. So it absolutely matters at what moment in time you are looking at this scenario, okay? Because it's going to change. The rate of change of the area is a changing rate of change, okay? Because it's dependent on something that changes, namely the radius, okay? Even though the rate of change of the radius with respect to time is constant, the radius itself is not, okay? So you have to be specific when you're talking about these things. This numerical value is the rate of change of area with respect to time when the radius is 36 inches or 3 feet, okay? So all of that matters. Okay, so you were fishing, right? That was what we were doing. We were fishing, okay? So let's actually get back to the fishing, okay? So you get a bite. You reel in the fish at a constant rate of 2 feet per second, and soon you notice that instead of catching a ginormous fish, you actually caught a big bicycle tire floating near the surface of the water. Lame. Okay, but you got to get it in, right? Because you need to actually try to catch some fish. So at first the tire moves slowly, and then you notice that it appears to move faster and faster as it approaches the dock. Okay, the dock you are fishing on is 3 feet above the water, so you estimate that your reel is also at this level. And what do you want to know? You want to know how fast is the tire moving towards the base of the dock when it is 20 feet from the dock. Okay, so do you have a visual image? With all of my artistic skills, I've got a dock. It's 3 feet above the blue water, right? And then you've got a fishing rod that's sticking straight out because you're working hard to reel in a tire. Okay? So here's a visual image of what's going on. So what's going on here? So here's my fishing wire, right? What do I know about this thing? Anything? I heard feet per second. That's all I heard. It's decreasing at 2 feet per second, right? Because you're reeling it in, right? So if I want to talk about that, in order to be able to talk about that happening, I need a label, right? I need something to talk about, okay? So I don't want to just talk about that thing is decreasing at a rate of 2 feet per second. You need a way to talk about it mathematically. So what do you want to call the length of this wire? L? We're going to call it L, okay? So mathematically, how do you explain that you're reeling in the fish, or the tire, at a constant rate of 2 feet per second? They tell you that dl dt is it 2 feet per second? Is L increasing or decreasing? If you're reeling it in, is L getting longer or shorter? Shorter. So is the rate of change positive or negative? Negative. So this should be negative 2 feet per second, right? Okay. What are they asking us about? Sorry, it's not on the screen. You have to look at your piece of paper for the question. The question was, how fast is the tire moving towards the base of the dock when it's 20 feet from the dock? Yeah, so how fast, let's call it X, right? So how fast is the tire moving towards the base of the dock? So maybe I shouldn't have drawn my fishing rod sticking out. Let's make the dock go to here, okay? So we want what? I want dx dt when what's happening? So again, the question is, how fast is the tire moving towards the base of the dock when it is 20 feet from the dock? Okay, how do I say that mathematically? When x equals 20. Okay, bless you. Okay, so we're given a rate of change of L. We want a rate of change of x. So the quantities involved are x and L, right? So what do we know that relates x and L? This is a right triangle, right? So x squared plus 3 squared equals L squared. What can we do now? Calculus. Okay, we have a formula now relating the quantities that we care about. We cared about them because we wanted to know the rates of change of them, right? Or we were given a rate of change of one of them. Okay, so let's do some calculus to introduce these rates. So if I take the rate of change of the left-hand side, what do I get? 2x? Is that all I get? So what am I taking the rate of change with respect to? Time. So the rate of change of x squared is not just 2x. Because remember, x is changing with time. So you have to use the chain rule and multiply by the rate of change of x with respect to time. What's the rate of change of 3 squared? 0. What's the rate of change of the right-hand side? 2L dl dt. Because again, L is also changing with respect to time. L is a function of time. Okay, so you have to use the chain rule when you find the rate of change. Okay, so what did I want again? I wanted dx dt when x is 20. So I can say dx dt is, divide both sides by 2, divide both sides by x, I get L over x dl dt, right? So in order to actually find my answer, my solution, right, I need dx dt when x is 20. But oh shoot, the very first thing I need to plug in is L. How am I going to find L? I can come back and use this guy, right? So if x is 20, when x is 20, what is L? Square root of 409, right? Technically, you get plus or minus when you solve that equation algebraically, right? Why isn't it minus? L is representing a length. Can't have negative lengths, right? There's no such thing as a negative square root of 409 feet of wire. Yes? Just the 2's canceled. Yeah, and then I divided x over, which is why I got L over x, right? So we get the square root of 409 divided by 20 times negative 2, right? Because dl dt was negative 2. So does it make sense that we got a negative number? What does this number represent? What does it represent? Scott? Yeah, so it's the rate of change of the distance of the tire to the dock, right? When the tire is 20 feet away. And since we're reeling it in, that rate of change should be negative because the distance between the tire and the dock is getting smaller, right? So it should make sense that we got a negative number. What are the units on that number? Feet per second. Okay. Now there are many, many more problems to do. Okay, but we are out of time for today. But you have a plethora of practice on MyMathLab. Okay, due Wednesday. So make sure you practice those, and make sure that if you have questions about your mastery test, or even if you don't think you have questions about your mastery test, come see me anyways, and let's talk about it. Okay?
I just had a quick algebraic question.
Okay.
So when you divide x over, why don't you have to divide the entire